I'm Dorian Rudolph and I present the talk on polynomially many queries to NP or QMA oracles, which is joint work with Sevag, Gharibian at Paderborn University. Note that I will explain basic quantum computation later, so in principle no quantum background is required. First, I go over the motivation for this research and prior work. One may ask the question, what lies beyond NP? Stockmeyer defines the polynomial hierarchy, which basically is the union of complexity classes P, P to the NP, P to the N, P to the NP, and so forth. Most relevant to our results is the second level of pH, delta 2P or P to the NP. Generally, we say P to the C for the complexity class that can be solved by a polynomial time Turing machine with access to an oracle for a C-complete problem. To gain an intuition, note that co-NP is contained in P to the NP because the Turing machine can perform the corresponding NP query and then output the negated answer. We can define further complexity classes by restricting the queries the Turing machine is allowed to perform. For instance, we can restrict it to a logarithmic number of oracle queries. The resulting complexity class is called P to the NP log and has the following complete problem due to Wagner. Does the solution to a max k-set instance have even Hamming weight? To solve that with a logarithmic number of NP oracle queries, first determine the maximum number m of satisfiable clauses using the binary search with oracle queries of the form, does there exist an assignment satisfying at least s clauses? Then ask whether there exists an assignment of even Hamming weight satisfying m clauses. Another kind of restriction is to require the Turing machine to ask all oracle queries at the same time. Hence, the queries are non-adaptive. They cannot depend on each other. It has been shown that this class, denoted P to the parallel NP, is equal to P to the NP log, which we'll also sketch later in this talk. Recall that P to the NP generally permits adaptive queries. So the ith query potentially depends on the answers to all prior queries. We can model these dependencies as a DAG. Here Qi is the ith query. In general, this DAG might be complete. In the case of non-adaptive queries, there are no edges between nodes. To construct a connected query graph, we add an output node that simulates the Turing machine and returns its output. By placing restrictions on the query graph's structure, we can define complexity classes between P to the NP and P to the parallel NP and P to the NP. Gottlob considers the restriction of query graphs to trees and defines the class trees of NP of problems solvable by a query tree and shows that this class is equal to P to the NP log. In the quantum world, we have the quantum analog of NP called QMA, Quantum Merlin-Arthur, which I'll define later. Kitaev proves a quantum Cook-Levin theorem by reducing QMA to the k-local Hamiltonian problem, which I now describe, though its understanding is not integral to the rest of the talk. We are given a Hermitian matrix H of dimension 2 to the n, which is a sum of k-local terms Hi, each acting on at most k qubits. We accept if the minimum eigenvalue lambda min of H is below a given threshold alpha. This is a relevant problem in physics, as H describes a quantum n-body system and lambda min of H its ground state energy, or the energy of the system when cooled to absolute zero. P to the QMA log also has a complete problem called APX-SIM, or approximate simulation, which was shown by Ambines. The problem is to perform measurements on the ground state of a k-local Hamiltonian. So here we are interested in properties of the ground state itself rather than its energy. A natural question is now whether the results for P to the NP log also have analogs for P to the QMA log. Gharibian, Piddock, and Yerka show that p to the QMA log is equal to p to the parallel QMA, just like in the classical setting. However, it was previously not known whether QMA query trees can also be solved with a logarithmic number of QMA queries. Next, I'll go over the results of our work. We define CDAG as the class of query graphs of bounded separator number at most s. Here we look at a constant separator number s equals to O of 1. Separator number is a graph parameter which is bounded by tree width, which I'll formally define later. Query graphs of bounded depth are called CDAG-D. Again, we consider a constant d here. Note that we use the term CDAG to either refer to instances of query graphs or to the class of problems that can be solved by such query graphs. Now let's compare the new results with the previous state of the art. In the classical setting, we have Gottloob's result on query trees from 95. We improve this to graphs of bounded separator number or tree width. For QMA, we had the result that p to the parallel QMA is equal to p to the QMA log, which we also extend to query graphs of bounded depth and separator number for a variety of complexity classes. One of the main challenges here was dealing with the promise setting of QMA, which is a class of promise problems. As a side note, our techniques are generally applicable to MA-like classes. However, in the case of stochastic MA, which I also don't define here, we can only improve the previous result to query graphs of bounded depth, and not bounded tree width, because it is not known whether the completeness or soundness parameters of stoch MA can be amplified to a constant gap. More concretely, our main result is that for these listed complexity classes here, a CDAG of separator number s can be decided with a deterministic Turing machine in 2 to the s times log n time steps and with s times log n c queries. Bounding the separator number by a constant, we obtain the aforementioned containment of CDAG s in p to the c log. If we allow a polylogarithmic separator number, we get a quasi-polynomial time base and one extra log factor in the query number. For query graphs of bounded depth, we obtain a very similar result with the same time and query bounds. However, we do achieve a polynomial time base for NP, NEXP, and QMA-EXP. Again, bounding d by a constant, we show that CDAG-D is equal to p to the c log. Kitaev uses a circuit to Hamiltonian mapping in his quantum Cook-Levin theorem to embed a quantum circuit computation into a Hamiltonian. The lifting lemma due to Watson, Bausch, and Gharibian then embeds non-adaptive QMA queries into APX-SIM, preserving certain geometric properties of the underlying circuit to Hamiltonian mapping, such as locality. The idea behind these geometric properties is to make the Hamiltonian more like a natural physical system. We extend this result to a generalized lifting lemma. In a simplified form, there exists a polynomial time many-one reduction from query graphs of bounded separator number or depth to APX-SIM, satisfying the geometric properties of the circuit Hamiltonian mapping HW. The main improvement over the previous result is that we can now lift query graphs directly and not just parallel queries. Now I will introduce some more formal definitions. I would like to start with a brief introduction to quantum computation. The state of n qubits is expressed by a complex unit vector, ket psi, which is this symbol here, of dimension d equals 2 to the n. The ith standard basis vector is written ket I, and for a classical n-bit string x, we write the corresponding standard basis vector as ket x. The Hermitian transpose of a vector psi is then written as bra psi, which is this symbol here. Quantum circuits apply unitary operators on quantum states. Unitary means that the Hermitian transpose of U is equal to its inverse. Generally, we deal with k-local operators V, which means that V can be written as the tensor product, also known as Kronecker product, of a k-qubit unitary U and an identity. Here, U then only acts on a subset of k qubits. The reason for using local operators is that they can be represented and implemented efficiently. In quantum computation, we can also measure states, which is modeled by a POVM, positive operator valued measure, consisting of a set of positive semi-definite matrices Mi that sum to identity. The probability of achieving outcome I is then given by bra psi times Mi times ket psi. For example, the probability of getting a 1 when measuring the first qubit standard basis is given by this expression here, where 1, 1 projects the first qubit onto 0. As mentioned before, the quantum analog of NP is QMA. Due to the probabilistic nature of quantum mechanics, QMA is a class of promise problems. Promise problems are just like languages with the addition of invalid query strings that are neither yes nor no instances. A problem pi is in QMA if there exists a uniform polynomial time circuit family Qn such that for all yes instances there exists a proof psi such that Qn accepts x together with the proof with probability at most 2/3. And for no instances, Qn accepts with probability at most 1/3 for all proofs. Note that this definition is just like MA, but with quantum circuits instead of classical. The constants 2/3 and 1/3 may also be replaced with thresholds alpha and beta, that the promise gap alpha minus beta is at least an inverse polynomial. Our results also hold for variants of QMA, like quantum classical QMA, QCMA, where the proof psi is a classical bit string, or QMA2, where the verifier is given 2 unentangled proofs. We can also think in terms of having 2 independent provers. Now let's define what a QMA query graph is more formally. In the rest of this talk, we mainly focus on QMA, but if you're not quite comfortable with that, you can also drop the Q and assume a classical MA. Each node in the DAG contains a QMA verifier Qi. Each Qi receives as input a string Zi of the outputs from incoming edges. For example, Q3 receives x1 and x2 as Z3. Qi also receives a quantum proof psi. The verifiers implicitly define promise problems pi in QMA, determining their output xi. So if xi is equal, so we set xi to 1 if zi is a yes instance, to 0 if it's a no instance, or if zi is an invalid instance, then xi can be either 1 or 0 non-deterministically. Hence, there can be multiple correct query strings x. But if x is a valid yes instance or no instance of a query graph, then its output must always be 1 in the yes case or 0 in the no case. Recall that Gottlob shows that trees of NP is equal to p to the NP log. We want to prove a similar result for more general graphs. Here, the parameter that comes to mind is bounded tree width, as such graphs are almost trees in some sense. In fact, we use a slightly more general parameter, which is called the separator number. The separator number S of G is defined as the minimum S, such that every subgraph of G has a balanced separator of size at most S. By balanced, we mean that after removing the separator, each connected component contains at most a constant fraction of the remaining nodes. One can show that the separator number is bounded by tree width, which in turn is bounded by log n times the separator number. However, we do not know if these bounds are tight. If a graph has separator number S, then we can recursively decompose the graph into a separator tree in which nodes are separators of the subgraphs induced by its descendants. On the right side, you can see an example query graph. Its output node is Y2. The separator tree is indicated by the dashed lines. For example, U1 and U2 form a balanced separator. Note that the edges here do not necessarily have to follow the tree structure, so an edge from x2 to u2 would also be allowed. Next, I will sketch the proof that QMA graphs of bounded separator number are p to the QMA log complete. To illustrate the basic approach, I begin with proving the simpler result p to the np log is equal to p to the parallel np. In general, p to the c log is contained in p to the parallel c. Suppose there are k adaptive oracle queries, then there are 2 to the k different computation paths in total. For logarithmic k, we can then pre-compute all these computation paths in polynomial time non-adaptively. The other direction is slightly more involved. We need to simulate the non-adaptive queries q1 to qn with a logarithmic number of adaptive queries. So suppose we are given proofs y1 to yn, define the query string x, with each xi is the output of running the verifier corresponding to qi with proof yi. We say x is a correct query string if it encodes the correct answers to all queries. For NP, the unique query string of maximum Hamming weight must be correct, because then all queries for which there exists an accepting proof are satisfied. We can compute the maximum Hamming weight using simple binary search. And we use a similar approach for other complexity classes like QMA, but there we have to deal with invalid queries and probabilities. Another important technique is flattening trees, which Gottlob uses to prove that trees of NP is equal to p to the NP log. For reasons discussed later, graphs with long paths are hard to deal with. For example, if we have a chain of queries u, v, w, then we can transform this chain by creating 2 copies v0 and v1 of v, in which the input from w is hard-coded with a constant 0 or 1. Then a node u' is created from u that selects the copy of v depending on w's output. For example, if w outputs 0, then u' uses v0 as v. Now let's get to the p to the QMA log completeness proof for QMA DEX of bounded separator number. The first direction is easy again, as p to the parallel QMA computations can trivially be modeled as a query tree as seen in the beginning of this talk, with a separator number of 1. To show the other direction, we need to construct a p to the QMA log machine evaluating a query graph G of bounded separator number. The first step is to define a weighting function for query graphs to prioritize important queries. For parallel NP queries, it was sufficient to maximize the Hamming weight of the query string. But in a graph, we need to give more weight to nodes with more descendants. Given a query string G, we compress it into an equivalent G' such that weights are polynomially bounded, permitting us to perform efficient binary search. Then we define the total solution weight function, assigning a weight to a set of query proofs and outcomes. This corresponds to the query string's Hamming weight in the previous example. We show that QMA queries can approximate the maximum value of this function and that only the correct query string maximizes it. Finally, we compute the maximum weight with a logarithmic number of QMA queries using binary search and then a query string x of that weight. The final result is then the output node's output xn. We use the same basic proof structure as Gottlob in his trees of NP proof, but with a novel graph transformation and total solution weight function adapted to probabilistic promise classes. Following this roadmap, we begin by defining the admissible weighting function. We say a function f, mapping from the nodes v of a query graph G to the real numbers, is C admissible if for all nodes v, f of v is at least 1 plus c times the sum of weights of all outgoing neighbors of w. So we can see that the weight on v exceeds the weight on the neighbors times c plus 1. This definition is the same as Gottlob's, but with an added factor of c. For example, The weighting function omega of v, defined as 2 to the c to the v up arrow, is c admissible, where v up arrow denotes the set of nodes reachable from v in G. So nodes with more descendants get a higher weight. In fact, an exponentially higher weight. If every node only has a logarithmic number of descendants, then omega is polynomially bounded. Unfortunately, there exist graphs for which any admissible weighting function is exponentially large, for example a simple path even. Therefore, the next step is to transform the graph to bound the number of descendants logarithmically. Here we have the familiar example again. The basic approach is to create copies of every node conditioned on nodes above and in the same separator, similar to the previous example from Gottlob. An output node T is also added, but we can ignore this for now. For the node x1, which is here, we create copies x1 to the z1, z2, z3, conditioned on outputs z1, z2, z3 of u1, u2, v1, v2, x1, and x2. Each Zi corresponds here to the outputs of nodes in one separator. So for example, z1 denotes the outputs u1, u2. And for example, we can see how x1 is only conditioned on the outcomes of outputs of nodes that are in separators above or in the same separator in the separator tree. It may seem odd to condition a computation on its own outcome, but that is only to simplify the construction. Every copy only has outgoing edges to nodes above it or in the separator tree. Therefore, v up arrow is bounded by s times d equals O of log n in the case of a balanced separator tree of constant separator size. Hence, the weighting function omega is also polynomially bounded. Copies in the separator tree need to determine which copies of their inputs to choose. For example, u1 depends on x2. Therefore, the copy u1 to the z1 of u1 has to compute the correct values z2 and z3 conditioned on z1 to determine which copy of x2 to the z1, z2, z3 to choose. Similarly, the output node now computes the correct values z1, z2, z3 to choose the correct copy of the output node y2. So we have created multiple copies of each node, which leads to an inconsistency problem. This is no issue with languages such as NP because every node either outputs 1 or 0 deterministically, but promise problems can cause a problem here. In this example, we have one invalid query at the bottom, followed by two queries that act as identities passing their input to their output, and an XOR as output node. Clearly, the output node is always 0, regardless of the invalid query's output. However, if we create two copies of the invalid query, both may have a different output, in which case the XOR would output a 1. The solution is to merge redundant copies, such that only one copy is used in an actual computation. So this is our merged query graph. For example, since x2 only depends on x1 and v1, we merge all copies differing in other bits in the conditioning string. So this is indicated by these asterisks here, so only 2 bits remain in the conditioning string. All other copies are merged. Next, we define the total solution rate function. Recall that this function is needed to enforce all queries in the graph to be answered correctly. So, given a query string x and proofs psi1 to psi_n, define the total solution weight as the sum of all queries, with the weight f of vi here, times this expression called gi. For xi equals 1, gi outputs the acceptance probability of qi on input zi, which is implicitly defined substring of the query string x, and the proof psi_i. If xi is equal to 0, then GI just outputs a constant gamma, which is the average of the completeness soundness thresholds alpha and beta. The intuition behind GI is that it penalizes an incorrect xi. If Zi is a yes instance, but we have a 0 as xi, then we have the value gi here is equal to gamma, which is smaller than gi. In the yes case, where we have a 1 here, which could be at least alpha for the correct proof. If Zi is a no instance, then gi with the 1 gives us at most beta, which is smaller than gamma for all proofs. And we can see that the penalty for a wrong xi is now delta, which is half of the promise gap. Finally, we define t as the maximum value of a capital T as the maximum value of t over all query strings and proofs. Next, we show that we can approximate t with QMA queries. Formally define the promise problem pi, deciding whether t is larger than s or smaller than s minus epsilon. For a total weight w, for a polynomial total weight w and an inverse polynomial epsilon, pi is contained in QMA. And the proof, we construct a verifier v with proof space x y1 to yn corresponding to query string and proofs. V first measures x in standard basis to obtain a classical query string x. Then it selects I with probability pi proportional to the weight on vi. If xi is equal to 1, it simulates the circuit qi with input zi and proof register yi. Else it outputs 1 with probability gamma. One can now show that the maximum acceptance probability of v over all proofs is precisely equal to t over w. The next step is to show that the maximum weight does indeed imply a correct query string. Formally, we show that if t of x, psi1 to psi(n) exceeds t minus delta, then x must be a correct query string, if f is 1 over delta admissible. Now suppose that xi is incorrect. Let xi prime be the fixed value and choose psi prime to maximize the difference between gi of xi prime and gi of xi. As seen previously, by fixing xi, we can increase gi by at least delta. However, changing xi may decrease gj of neighbors vj of vi. Due to the definition of the admissible weighting function, we know that f of vi times delta exceeds the sum of weights on its outgoing neighbors vj by at least delta. Finally, we compute the maximum weight with a logarithmic number of QMA queries using binary search and then a query string x of that weight. The final result is then the output node's output xn. The generalization to other complexity classes is straightforward. However, for stochastic MA, this is not so easy because we did have to use the fact that QMA can be amplified, which is not known for stoch MA. Next, I will show the basic construction of the generalized lifting lemma. First, we need to define the approximate simulation problem or APX-SIM. Given a k-local Hamiltonian H, an observable A, numbers alpha, beta, epsilon, such that beta minus alpha and epsilon at least inverse polynomial. In the yes case, there exists a ground state psi of H such that psi has energy at most alpha with regard to A. In the no case, all psi of energy at most lambda plus epsilon, so lambda is the minimum eigenvalue of H here, have energy at least beta with regard to A. To restate the generalized lifting lemma, we want to construct a many-one reduction from CDAC-S or CDAC-D to APX-SIM for constants D and S, using the given circuit to Hamiltonian mapping HW and preserving its geometric properties. To construct the APX-SIM instance, recall the verifier computing T. It first selects I with probability Pi. Then, if xi is equal to 1, it simulates a circuit qi, and otherwise it outputs 1 with probability gamma. In this diagram, we denote this output by Q flag, or the flag qubit. Xn here is simply the last bit of the query string, corresponding to the output of the query graph. The ground state of the Hamiltonian from the circuit to Hamiltonian construction, HW of V, is simply the history state phi, which is a superposition of intermediate states in the computation of V. Here each Vi is one gate of V. We define the APX-SIM instance with a Hamiltonian H is equal to alpha times HW of V plus the projector of Q flag onto 0 times the projector onto the last time step of the computation. Alpha here is some suitably chosen constant, which I'll not go into detail on. The observable A just projects Xn onto 0. The ground state of H is then the history state with initial state phi0, so this corresponds to that one. Where phi0 then contains the parameters maximizing t. Here HW ensures that the ground state of H is indeed a history state of this form. And projecting the flag qubit onto 0 ensures that the ground state here maximizes t. A then can check whether the computation is accepting or rejecting. To conclude the talk, we discuss some open problems. Can we extend our results to further classes such as QMA1 with perfect acceptance probability, or UQMA with a unique accepting proof, or stochastic MA where we are not able to show all our results? What is the exact relationship between separator number and tree width? Can separator number ever exceed separator number? Can tree width ever exceed separator number by more than a constant factor? Can we compute separator trees or approximate separator trees more efficiently? Because for a bounded separator number, a simple brute force approach is sufficient. However, there also exist graphs with a constant size separator tree, but a logarithmic separator number. In that case, we don't know how to compute the separator tree efficiently. Lastly, we show that for a polylogarithmic separator number, T-S is contained in QP, or quasi-polynomial time, with polylogarithmic C queries. Is the quasi-polynomial time base really necessary here? And thank you for listening. Feel free to send any questions to my email.